Hello viewers, good morning. Myself Dr. T.N. Ojha, retired professor of chemistry. Today I am going to discuss a very important topic of spectrometry called microwave rotational spectrometry of diatomic molecules. In short, we call it MRS. The points to be discussed here are introduction to MRS, derivation of pertinent equations, quantum mechanical derivation, instrumentation, oscillator strength and intensity considerations, deviation from the classical equation and correction thereof, rotation vibration combined, applications of MRS. You must be knowing this topic is included in the syllabi of undergraduate as well as postgraduate classes. It is very important and the topic is simple also. Therefore, I have chosen to discuss it in a bit detail. And the last, we will give some problems for revision purpose. So first, let us understand what is meaning of molecular rotation. The whole body rotation of a molecule, that is the spinning of a molecule about an axis called the rotation axis, which passes through its natural center of mass, also called center of gravity. This kind of motion is described as molecular rotation or molecular spin. It is associated with quantized energy states which are defined by the rotational quantum number symbol J, and J has integral values ranging from 0, 1, 2, 3, etc. up to infinity. Absorptions of far infrared radiation and microwave radiation by the molecules in the range of 1 reciprocal centimeter to 100 reciprocal centimeter. Gas phase molecules, which are polar, produces pure microwave rotational spectra, MRS. This spectra is also called line spectra because it is pure. The lines are distinct, discrete. Liquids and solids having appreciable vapor pressure can also be examined for this technique, but those possessing no dipole moment, that is having dipole moment zero, cannot be examined by this method. However, such molecules which don't have dipole moment can be examined by the method of Raman spectrometry, which we will discuss at a later stage. Microwave rotational spectra of viscous liquids and solids are not suitable. The reason is their rotational energy states no longer remain sharply discrete but get blurred due to the rampant mutual collisions and consequent changes in their electronic clouds, hence in their state function, wave function. The in nutshell we can say that if the sample is viscous liquid or it is solid, their rotational energy levels are not discrete, they are blurred out. So we cannot define them sharply and we cannot solve the quantum mechanical expression. The spectra of simple molecules which are having dipole moment can be interpreted, but again, the spectra of complex molecules cannot be properly interpreted. Therefore, this technique of microwave rotational spectrometry is applicable to what type of molecules? First, permanent dipole moment is a must. Second, gas phase. Third, simple structure or complicated molecules. This technique is not applicable. When we examine the microwave rotational spectra, what we see there, we find a number of equidistantly placed sharp absorption lines, and the separation between two adjacent lines is given to B. What is B? This is called rotational constant of the sample molecule. At later stage, we will define B. The B is the parameter which can be obtained from the spectrum, and from B, we can further calculate bond distance. Here, I have shown the model and defined some important terms. See, there are two atoms A and B. The distance between A and B, that is bond distance, is R. P is the center of gravity or center of mass. The distance of atom A from center of gravity is shown as R1. The distance of atom B from center of gravity is shown as R2. R1 plus R2 gives the bond distance R, which is shown below. Now, the molecule is rotating about an imaginary axis passing through the point B, P. The rotation could be clockwise or anti-clockwise, both are equal energy rotations. The only thing is, if the molecule possesses dipole moment, then it is of interest to us. Here this figure shows end-to-end rotation of this diatomic molecule about its center of mass marked P. Bond distance as shown in equation 1 is equal to R1 plus R2. Another term, momentum conservation. It says that M1 R1 equal to M2 R2 or MA R1 equal to MB R2. From this simple relationship, we can have MA R1 equal to MB R minus MB R1. From this, we can determine the value of R1, which is given to MBR divided by MA plus MB. Likewise, we can determine the value of R2, MAR divided by MA plus MB. Why do we need these values of R1 and R2? Because R1 and R2 are imaginary quantities. We don't know where the center of mass of the molecule lies. Therefore, we must remove these quantities which cannot be measured. We cannot measure R1 and R2 by any means. Therefore, in the equation, we need to eliminate R1 and R2 by a parameter which is known, which is bond distance. R is known, R1, R2 can never be measured. Therefore, we need to replace them by mathematical relationship. Now, another term we will define, moment of inertia. I, symbol is I. It is equal to MA R1 square plus MB R2 square. This is for a diatomic molecule. If we have a large molecule having several atoms, then moment of inertia is given by sum of all the terms. Here we have only two atoms, therefore we have taken sum of only two terms. Now we will simply replace R1 square and R2 square as we derived their values earlier. So finally we find the expression I equal to mu R square, where mu is moment of inertia, mu is reduced mass, and R is bond distance. Now see, why do we derive this expression? Mu is reduced mass, MA multiplied by MB divided by MA plus MB. We can know this quantity because we know the atomic weights of atoms A and B. Bond distance, we are interested to measure the bond distance. So what is the final purpose of getting this equation? We have removed the unknown quantities R1 and R2 by quantities which can be measured. So I equal to mu r square is a very, very important expression. I is moment of inertia, mu is reduced mass, r is bond distance. Now linear velocity and angular velocity. You know, linear velocity v1 for atom A is equal to r1 omega. Similarly, for the atom B, the velocity v2 equal to r2 omega. Here omega is angular velocity and omega is given by 2 pi n, where n is the rotational frequency and pi is a well-known constant. Yet another term we would define is L square equal to I square omega square. What is L square? L square is called linear momentum. It is given by the product I into omega. So therefore L square becomes I square into omega square. Why we have squared this will be clear at a later stage. L square, if you divide this L square by 2I, then the right hand side of expression will also be divided. And we get L square divided by 2I equal to I square omega square divided by 2I, which leaves behind I omega square over 2. This is the kinetic energy of rotation given the symbol ER. Kinetic energy of the system ER is given by I omega square by 2. I defined earlier, I is mu r square and omega is rotational angular velocity. As we know, the familiar equation, kinetic energy is mass into velocity square divided by 2. So the same expression we have used here, ER equal to MA V1 square plus MB V2 square whole divided by 2. This becomes equal to I omega square by 2. So we have determined an expression for the kinetic energy I omega square by 2. Then in quantum mechanics, L is defined by the expression given here, L square equal to h upon 2 pi whole square multiplied by j plus 1. J I have explained earlier, J is rotational quantum number having integral values. H is Planck constant, pi is constant. So the square of linear momentum L is given by this expression. As we know, L square is connected to kinetic energy. Therefore, we will replace the value of L square by this expression. Hence, we can define kinetic energy of rotation by L square upon 2I, replace L square by h square upon 8 pi square I, j plus 1. As we know, energy E is given by hc nu, where c is velocity of light, nu is frequency, and using this expression, we can have ER, that is kinetic energy, equal to V h c j plus 1 units of joule. What is B? We have actually collected few of the constant terms and given one simple symbol for that, so that we need not write those all those terms again and again. B is called rotational constant of the molecule. If we use frequency units, then the expression for energy unit has to be divided by hc, and we get frequency nu j or nu 1 equal to fj equal to bj plus 1 centimeter reciprocal. Rotational constant B has the value H upon 8 pi square I C in reciprocal centimeter units. Now here I have shown the energy of various rotational levels, rotational quantum number J, energy in units of joule, energy in units of frequency. When J is 0, that is the zeroth rotational quantum level, energy is 0. These molecules in the lowermost rotational quantum level don't possess any rotational energy. When we study molecular vibrations, there we will find a difference. Here J equal to 0 means no energy of rotation. There, when we talk of the zeroth vibrational quantum number, there the molecule will have some energy known as 0 point energy. So note this is very important difference between the two. When the value of J becomes 1, then energy becomes 2B in terms of frequency. Likewise, for J equal to 2, energy is 6B. For J equal to 3, energy is 12B. We are simply putting the values of J in the expressions given above. When J is 4, the value of energy becomes 20B. When J is 5, energy becomes 30B. And when J is 6, energy becomes 42B. What we have done here, we have simply put the integral value of J and obtained the energy in both. Here joule units and frequency units are used. Now the selection rules and condition for absorption of microwave radiation. All molecules cannot absorb microwave radiation. What are the conditions? The molecule must possess permanent dipole moment. And what are the selection rules? Means if a molecule absorbs energy and suppose it is present in the J level, then where will it go? It will go at the next higher level. That is why we have written here delta J equal to plus minus 1. Plus indicates absorption, that is going to upper level from the lower level. Minus indicates emission, that is coming from upper level to lower level. Again, for comparison, I have given here, when we study Raman spectrometry, there we will find delta J equal to plus minus 201. So both conditions are given here. For rotational spectrometry, delta J is plus minus 1 and mu AB not equal to 0. The molecule must possess dipole moment. If it does not have dipole moment, it won't be suitable for study by microwave rotational spectrometry method. Some examples of microwave active molecules: HX, H2O, NH3, etc. Gas phase samples are required to be used. And what is the spectral range? I have told it earlier also. Normally, 1 reciprocal centimeter to 100 reciprocal centimeter. But at this point, I must tell you, these days techniques have been advanced and high energy radiations are also used. But traditionally, the range included between 1 centimeter inverse to 100 centimeter inverse. These are the wave number units. You can readily convert them to frequency unit or wavelength units. And what do we calculate from microwave rotational spectra? We calculate I. We measure B. From B, we calculate I. I is equal to mu r square. Mu can easily be calculated from the atomic weights, and r square can be determined. R is equal to under root of I by mu, and I is moment of inertia and mu is reduced mass. We can put the value of V here to obtain R. Deviation from rigid rotor model. While deriving the equations given above, we have assumed that when the molecule is rotating, there is no effect on the bond distance. But by common experience, we know when the molecule is rotating at high speed, then it tends to pull the atoms away from the central point, from the center of gravity. It means that the equations derived earlier need some correction. The reason I have told you, the correction for centrifugal distortion, the value of this correction may be approximated, not exactly approximated, using quantum mechanics, particularly perturbation theory, which is an approximation method. The corrected equation is Fj equal to Bjj plus 1 minus Dj j square j plus 1 whole square. Here D is called distortion constant, and this is related to vibrational wave number. By the equation number 19 given here, Dj equal to 4B cube divided by V square, where V is wave number. Energy of rotational transition from level J to level J plus 1. As I told you earlier, if the molecule fulfills the conditions, that is dipole moment condition, and it is exposed to infrared, far infrared and microwave radiation, it can absorb radiation. Then what will happen? The molecule will be rotationally excited from a level given J to the next higher level, J plus 1. We need to calculate the frequency for this transition. So from the higher frequency, subtract the lower frequency, and finally we reach the expression 2bj plus 1. Rotational spectrum. You see, an idealized spectrum has been shown here. The rotational energy levels are not equidistantly placed. Listen this point very carefully. The rotational energy levels corresponding to J 0, 1, 2, 3, 4, 5, 6, etc. They are not equidistantly disposed. And the transitions between two adjacent levels are shown on the right side of the figure, from 0 to first, from first to second, from second to third, from third to fourth, from fourth to fifth, from fifth to sixth, and so on. Surprisingly, the separation between two adjacent absorption lines is to be constant. Therefore, we need not analyze the entire spectrum. We need to extract the value V from the spectrum. So we can pick up any two lines, juxtaposed lines situated nearby, and the separation between them is equal to 2B. Half of this becomes B. From B, we can calculate I. From I, we can calculate R using the equation I equal to mu R square. While deriving this equation, we have made certain assumptions. What are those assumptions? Let us see. First assumption is The molecule is a rigid rotor, means when the molecule is rotating, its bond distance is not going any influential change. Actually, this assumption is not true, but for mathematical brevity or sake of mathematical equation derivation, we have assumed this model. Secondly, fixed position of both atoms, that is bond distance constant. Actually, the books describe bond distance. Those are not constants. Those are equilibrium distances. Molecules are continuously rotating, continuously, even all phases, gas, liquid, solid. So, fixed position of both atoms, it is wrong to say like this, but for mathematical simplicity, we have to assume this. Fixed bond distance R. Again, this is an assumption, not true. Masses of both atoms A and B are replaced by reduced mass mu AB. Thus, the two particle system AB becomes simplified as one particle system. You might ask this question, when we are having two atoms having separate masses, why do we use reduced mass? When we use reduced mass, the two particle system has been simplified to one particle system. We need simple one wave function, and quantum mechanically it will be very easy to solve such an equation using Schrodinger wave equation Hi equal to Hi. This can be modeled and solved for the energy of rotation. Now let us consider a rigid rotor. We assume that the bond distance R is constant, so that any change in R, that is dr, must be zero. Remember this point. Because we have assumed bond distance R is constant, it means any slight change in bond distance, that is dr, D indicates very small change, so dr must be equal to zero. And the kinetic energy of the rigid rotor is given by the equation we described earlier, I omega square by 2 equal to L square by 2I. L is linear momentum, I is moment of inertia. Now we would like to set up Schrodinger wave equation Hi equal to E psi. H is the Hamiltonian operator. Its value is given here, minus H square upon 8 pi square mu del square plus Vr. Here Vr is the potential energy term. And this Laplace operator we have used here. It describes d2 by dx2 plus d2 by dy2 plus d2 by dz2. But here we are using a simple diatomic molecule. So only one term, x direction, will be used. In a spherical coordinate system, the Laplace operator is given by the following expression. Expression is written over here, 1 by r square d by dr, r square d by dr, plus other two terms. See here we are having three terms. One is in the form of r, that is distance, another is in the form of angle theta, and the third term involves the angle phi. Because the bond distance we have assumed remains constant, so the first term, which includes only the bond distance changes, becomes zero. I repeat this point. Earlier we assumed that during rotation, bond distance remains constant. So out of these three terms, the first term includes change in bond distance. When there is no change in bond distance, it means dr is equal to zero. When dr is zero, we can ignore this first term. We only have this second and third term. So we get simplified equation number 4. Alternatively, Hamiltonian can also be written as kinetic energy. You see in equation 2, we have potential energy term Vr. Because the diatomic molecule is not experiencing any force from outside, it means its potential energy is zero. Therefore, we have included only the kinetic energy term T. Here T is not temperature, remember. Here this T stands for kinetic energy operator. It is not temperature. So H is in the form of kinetic energy operator and equal to L square by 2I. Here, in a spherical polar coordinate system, L square is given in the terms of r, theta, and phi. R, I told you, measures the distance. Theta and phi, they measure the angle. And the value of L square in quantum mechanical value is given here by equation 6. Now, because we have defined Hamiltonian H cap, we can write now the full Schrodinger wave equation. The equation is given here, equation number 7. Multiplying both sides by minus h 8 pi square I upon h square, we can rearrange this equation number 7 further and we get equation number 8. Equation 8 is very important equation. Look carefully. This equation has two angular variables, theta and phi. Now it can be solved by the method of separation of variables. Solving further, it leads to the energy equation value given over here. This lambda is eigenvalue equal to 8 pi square IE upon h square equal to L plus 1. L is the quantum number. What we have to do, we will simply replace the symbol L by J. And the same expression, expression number 8, is applicable to rotational energy states. It is customary to represent the rotational quantum number by J. Therefore, the above equation becomes energy equal to J plus 1 h square upon 8 pi square I. Again, we use the simplified symbol B, rotational constant. So equation becomes BHCJ plus 1 in terms of energy. In terms of frequency, it becomes BJJ plus 1, where the value of B is h upon 8 pi square IC. Now we talk of instrumentation. The microwave rotational spectrometer is a complex assembly of so many units, so many parts, so many components. We need not go into the details of electronics. We don't require that. Here I have just given the names of various components and the sequence in which they are arranged. One is klystron. Klystron is the source of microwave radiation. Attenuator, wave meter, coupler, sample cell, detector crystal, oscilloscope for recording, frequency standard crystal mixture, radio frequency receiver, and dedicated computer. These are some of the components of the spectrometer. The actual spectrometer is a very complicated instrument, very costly also, and we don't require much detail about that. That becomes the subject of engineering. These days, Fourier transform technique is used. It's a very fast one, and the instrument is also very much sophisticated. Fourier transform, abbreviated as FT. Oscillator strength and intensity consideration. If we look at actual microwave rotational spectrum, we find a number of lines, but their intensities are not all equal. They are different. So how to determine those intensity and how to explain the difference in intensity? These are done using this concept, oscillator strength and intensity consideration. We define a term transition moment and oscillator strength. The rotational state transition from initial state I to the final state J, that is from quantum state J to J equal to 1 to J plus 2. It has a probability given by the transition moment integral defined below, mu ij, integral of psi 1, psi I star, then operator psi j dV. I will tell you the meaning of each and every term. Here, the cap over U is the dipole moment operator. Remember it. This cap over U indicates transition moment or dipole moment operator. dV is the volume element. dV equal to dx times dy times dz. D again, I tell you, indicates very, very small change. So dV is called volume element. It can be replaced by dx into dy into dz. Psi is the wave function. Psi I means initial state wave function. Psi j means final state wave function. Mu ij is the probability which can be given in terms of transition dipole moment integral. If the value of mu ij is 0, microwave rotational spectrum cannot be obtained. If its value is greater than 0, then only spectrum will result. The intensity of spectral lines is proportional to the population ratio Nj by N0. N0 is the total number of molecules in the sample. Nj is equal to the number of molecules present in the level J. Value of J could be any level, 0, 1, 2, 3, etc. And this factor Nj by N0 is given by the product of multiplicity of rotational lines and the Boltzmann exponential factor. Multiplicity, that is degeneracy of rotational levels, is given by 2j plus 1, indicated by the symbol gj. Therefore, nj by n0 becomes equal to 2j plus 1. This term indicates the multiplicity, that is degeneracy of the level j. And multiplication is done with the Boltzmann exponential factor, e raised power to minus ej upon kt. Ej refers to energy of that particular j level. And here T is absolute temperature. Replacing E by the HCF, we have the other equation in terms of energy. Finally, we derive equation 20. Nj by N0 can be plotted as vertical axis against the rotational quantum number J, which is horizontal axis at a given temperature. For example, you can choose a temperature 300 Kelvin or something like that. We should see that relative intensity passes through a maximum. It can be derived using this expression. The maximum intensity of a line J max is given by under root of kT upon 2 BHC minus half. This is statistical derivation we have not detailed here, but you must remember which line will be most intense line, at what quantum level the line will be most intense, J max. It can be calculated from this. K is Boltzmann constant, T is absolute temperature, B rotational constant, S Planck constant, C speed of light. For a typical case, the rotational constant B was found to be 1.566 reciprocal centimeter at 27 degrees Celsius. If we substitute the values, we can calculate J max value. You see, here plot has been given. Again, this plot I have taken from my own book of spectrometry. On the vertical axis, we have Nj by N0. Along the horizontal axis, we have the quantum number. You see, the graph shows a maxima somewhere, and the maxima can be calculated using the equation given above. Here, I have included the actual spectrum of carbon monoxide. You see, a large number of rotational absorption lines. All lines are not having the same intensity, but we Need not fear the complexity of the spectrum because what we need to measure the separation between two adjacent lines. That is all. That separation will be equal to 2b. From 2b, we can calculate b. From b, we can calculate I. From I, we can calculate R. It may be noted that rotational spectra are recorded in gas phase. Molecules are simultaneously both vibrating and rotating. As molecules are excited to higher rotational levels, their faster rate of spin increases the centrifugal force, thereby tending to push the atoms outward. This results into slight stretch of the bond, consequently, slight increase in the moment of inertia. As both the parameters B and I are inversely related, increase in the value of I leads to a slight decrease in the spacing between the J levels. The correction for the centrifugal distortion may be found through the perturbation theory. As I explained earlier, the equation was also given. Again, the equation is repeated here. dj is called vibrational centrifugal distortion constant, and it is related to vibrational wave number. Rotational vibrational combined. As I told earlier, the molecules are simultaneously rotating and vibrating. Therefore, we need an expression which is for both terms, rotation term and vibration term. Such an expression is the most useful equation. Rotational term is given by Fj Bj j plus 1 in units of reciprocal centimeter. Vibrational term plus an harmonicity term is given by here shown GV V plus 1 by 2 omega E minus V plus 1 by 2 the whole square omega E Xe reciprocal centimeter. Here I tell you what is this harmonicity constant. When we will study vibrational spectrometry, there I will tell you the bonds are not fixed, they are continuously stretching, vibrating. Therefore, some kind of inaccuracy enters into the classical equation, and that is called an harmonicity. That has been corrected over here. So we include three terms. The first term is rotational term, the second term is vibrational term, and the third indicates an harmonicity term. Here V is vibrational quantum number, again having integral values. If we combine these three terms, the frequency of rotation vibration combined is given by this expression shown below. And the selection rules are delta J equal to plus minus 1. Applications of microwave rotational spectrometry. You see, the spectra of simple molecules can be interpreted, but those having complex molecular structure are not amenable to any meaningful analysis because calculation of their moment of inertia is generally too much ambiguous, doubtful. The MRS of sample consists of many equidistantly placed sharp absorption lines separated by a factor of 2b, the parameter called rotational constant of the sample molecule. We obtain 2b from the spectrum. From B, we obtain I, and I is equal to mu r square. R is bond distance. Thus, R can be calculated. Secondly, a very important parameter, dipole moment, can also be calculated. And thirdly, by using isotopically labeled molecules, we can determine bond distances of molecules having more than 2 atoms. One very important application of microwave spectrometry is isotopic abundance of elements, particularly on other planets. Another application includes conformational energy barrier, their measurement, symmetry properties of molecules. So I repeat the applications. Number one, determination of bond distance. Number two, determination of isotopic abundance. Number three, determination of dipole moment. Number four, conformational energy barrier. Number five, symmetry properties. These are some of the applications, and this technique finds used in chemistry, geology, cosmology, environmental science, etc., etc. Here I have show conformation of ammonia molecule as a function of angle. See the beautiful picture. Ammonia molecule changing from one conformation to another, and below is shown the energy diagram against the angle of rotation. So the barrier can be measured using this microwave rotational spectrometry. Use of isotopically labeled molecules. As I told earlier, if there are more than two atoms in the molecule, for example, a triatomic molecule, we need to determine two bond distances. This is a bit complicated. We require isotopically labeled molecules, and the details are described over here. If we use isotopically labeled molecules, then the B value change slightly. And B by B prime, where B is for the normal molecule, B prime is for the isotopically labeled molecule. This becomes equal to I prime by I. Again, this can be replaced by mu prime R prime square by mu R square equal to mu prime by mu. Why? Because we assume that bond distances do not change when we are using isotopically labeled molecules. Although very accurate measurements have shown that slightly bond distance changes slightly, but at the moment we can ignore the change. We can equate R prime and R the same. By measuring B and B prime, we can calculate I and I prime, and therefore we can calculate their mu values. By taking an example, the method is explained into detail. We have taken an example of OCS molecule. In one case, it is sulfur 32. In the other case, it is sulfur 34. The molecule is rotating about the center of gravity, point P. Various parameters are shown here. Molecule A refers to the normal molecule, and molecule B refers to the isotopically labeled molecule. So for the normal molecule, moment of inertia I is given. Similarly, applying the concept of conservation of momentum, we find expression number 4. Rearranging question number 5. Again rearranging, we get question 6. You see, all this is mathematical jugglery. We are trying to replace unknown quantities by quantities which can be measured. This is the whole logic of mathematical modeling. We simply remove those quantities which cannot be measured from experiment. So we replace those quantities by those quantities which can be measured. So here we have obtained the value of R1. This value can be substituted in pertinent equations. This whole exercise allows us to determine bond distances where number of atoms is more than 2 in the molecule. Another point, microwave oven. You all have heard the name microwave oven these days being used as a kitchen appliance. How does it work and why it is preferred? The reason is very, very simple. The working of microwave oven depends upon the absorption of microwave radiation by the molecules of water which are present in the food. These rotationally excited water molecules in the food transfer their energy, excess energy, as heat to the molecule of food, which being large cannot rotate. The food molecules like proteins, carbohydrates, fats, they cannot rotate, but the water present in those molecules, water can rotate and water can absorb the microwave radiation. Now the heat it gains is transferred to the food molecule. So food is cooked without being exposed to higher temperature. It is cooked at normal temperature. Therefore, some of the essential components like vitamins and other things, they are not destroyed. That is the beauty of using microwave oven. Thank you very much.